Good morning, everyone. I'm going to talk about microzonation. I think I don't need this one. I should keep it away. Microzonation studies for City of Ottawa. First of all, I would like to acknowledge all of my co-authors, a long list from Carleton University, Air Science Department, Civil Engineering Department, Geological Survey of Canada. None of my students are here today, so I just wrote down a dozen of Carleton University students. As you are aware, National Building Code 2005 requires seismic site amplification in the building code is a required parameter, and seismic site classification and amplification is an important factor, has become an important factor for the City of Ottawa because 65% of the City of Ottawa are located on very loose soil. We call it leader clay. The shear wave velocity of leader clay is about as low as 150, on average, 150 meters per second. It's very low. And 20% of the city is located on the bedrock. The shear wave velocity of the bedrock is 2,700. If you look at the difference, 2,700, 150, the contrast is about 20, 18, 20. This is huge. This is unusual, okay? If you compare it to California or Western Canada, the contrast is around 3, 4. Here we have a contrast of about 20. And 15% of the city is located on glacial till, and the shear wave velocity average is 580 meters per second. This shows the distribution of the different geological units, and this shows the thickness of the soil in the City of Ottawa. As you see, in eastern part of the city, we have thick pockets of soil. This is the way that National Building Code of Canada classifies this site classes, soil classes. If it's class A, the shear wave velocity for the top 30 meters should be more than 1,500 meters per second. It's called hard rock. If it's 760 to 1,500, it's called rock. And eventually, if it's around 180 to 360, it's called soft soil. And if it's less than 180, which is the worst site class, it's called class E, which is very soft soil. And this is the table given by National Building Code. The reference level is for C class is 1, and for class A is 0.5. For class A is, let's say, 2. If you divide this one, class E by class A, is a factor of 4 difference between whatever you feel or the building feels on the soil compared to whatever it feels on the nearby bedrock. So because this is an important issue for Ottawa, we have started working over a few last years. One of the survey that we have done is downhole measurements. Simply we just send a sensor down in the borehole, hammer the ground, find the travel time, and just every half a meter or 1 meter, we just move this one up and do the measurement again and come up with the shear wave velocity of the soil. We covered 18 sites in the City of Ottawa. This is the location of those sites. The second method that we use is very popular these days. It's just a seismometer, launch bag size. This is the size of the box. Just put it there, 20 minutes, record background noise, nothing else. A passive method. 3 component, you have horizontal component, vertical component, find the spectrum of the horizontal divided by vertical. If you are lucky, you get a peak, something like this. And this peak is the fundamental frequency of the soil that you do the measurement on it. This fundamental is related to shear wave velocity of the soil and the thickness of the soil. It's very fast. 20 minutes, we just do the recording and move to the next site. Some people say it's accurate. I'm going to talk about the accuracy of this method. And this is one of the best methods that we can use in Ottawa, mainly because the contrast ratio, as I mentioned, is 20. And we can get this peak very sharp. When you have the contrast ratio around 3, 4, 5, you can find this peak easily. And we are lucky to have this contrast ratio as for this measurement, not for the seismic wave. This is the location of 400 sites that we covered in the city of Ottawa. Another method that we use is seismic reflection refraction. Simply, we plant 24 geophones, spacing 3 to 5 meters, connect all of them to a seismograph, and do the recording, hammer the ground, and come up with the shear wave velocity as a function of depth for the soil. This is accurate, and 2 or 3 sites per day can be done, each site 4 or 5 hours. 2 or 3 hours. So this mainly is done in city parks and road sites. This is a high-tech method. This is a mini vibe. And we simply drag 24 or 48 3-component geophones on the pavement, on the street. And every 3 meters, the mini vibe stops, starts shaking the ground with a specific frequency. And these geophones record the shaking, and we come up with the shear wave velocity depth function, and as this one moves. So using this method, which is an expensive method, we can cover 3 to 5 kilometers per day in the city, on pavement. We have covered 25 line kilometers of using this land streamer in the city of Ottawa. This map shows the location of all of those 700 sites, seismic reflection refraction, and 25 line kilometers of mini vibe or land streamer, and also 43 MASW method. Okay, these are geophysical methods that we apply to come up with the shear wave velocity depth function for the leader clay, to come up with the average shear wave velocity of the glacial till and the average shear wave velocity of the bedrock. This is about 9,000 data points, shear wave velocity as a function of depth for leader clay. Using this method, we came up with this simple equation, which simply gives you the shear wave velocity as a depth for the city of Ottawa for the leader clay. And the shear wave velocity of glacial till, 580 plus minus 175. Glacial till, usually we don't have it. If we have it 1, 2, or 3 meters on average. And the shear wave velocity of the bedrock on average is 2,700 plus minus 675. We have very high shear wave velocity bedrock in Ottawa. We have this is a typical site. If you have 20 meters of soil, 5 meters of glacial till, and the bedrock, you have this profile. We apply this equation to a large number of old boreholes. We have 32,000 boreholes available in the city of Ottawa. We trimmed it down to 21,000 quality boreholes that we are confident about the quality of the boreholes. This shear wave velocity profile that we got for different geological units, we applied to each individual borehole in the city of Ottawa, and we came up with the shear wave velocity or V-steady map for the city of Ottawa. As you see in the eastern part, this is the Orleans area. We have the worst site class, which is class E. Some people say it's class F as well. And in just 200 or 300 meters, you move from class A, which is the best site class, it's on the bedrock, to the worst site class, which is class E. This is one of the applications of the VS30 map that we provided for the city of Ottawa. This is the seismic hazard map for the city of Ottawa based on National Building Code of Canada. And this is for 5 years, 2% in 50 years exposure time. This is if I multiply the value given in this map by amplification factor for each site class, This is site class A, B, C, D, and it's color-coded here. Multiply this map by this map, I get this seismic hazard map, which right now, in this case, is the site amplification factor, based on those factors given in National Building Code of Canada, is included. This is why we call it microzonation, seismic microzonation. And another application is University of Western Ontario. Gale is using this map for shake map and early warning system, earthquake early warning system. If you are interested in gory details of all of those geophysical methods, interpretation, this is the GSE open file. It's quite a few gig, big file. You can download it, or you can ask. We can send it on the DVD to you. And we published a paper on this one last year, a few months ago. It's in the Canadian Geotechnical Journal. And we provided, I'm not sure this link is working, or is it connected to internet, or no? No, okay. So the map that you saw is available on Google Maps, something like this. You zoom in, just typical Google map that you have it. You zoom in, you'll find, if you're located in Ottawa, you find the location of your house or building. You can find the site class. You can find the nearby borehole, available borehole, or any seismic site that we have done. This is an interactive map that you can activate, deactivate all of these information and find your house, and it's available, it's open to public, and is on the Carleton University server right now. In National Building Code, site amplification or site classification is based on VS30, the average shear wave velocity for the top 30 meters of soil or rock, both of them. Recently, some people say, okay, this is mainly for California. And some of building codes are trying, or they are thinking, or some of researchers are thinking to classify seismic sites based on the fundamentals period or fundamental frequency. It says that the VS30 is not the best representative of the seismic site amplification. Maybe we should also include the fundamental site period. This is why we have started working on the fundamental site period or frequency for the city of Ottawa using different methods that I'm going to talk about. One of them is just a background noise analysis. This is, again, the same lunchbox instrument that I talked about. You just go there for 20 minutes, measure the background noise, and come up with fundamental site period or frequency. Or you can use the earthquake recordings or equivalent single layer. This is the method which is recommended, or it is in the National Building Code of Canada. It's just simply you model the soil as a one layer and come up with the fundamental site period. Multi-layer, this is another method that we use, and finite fault modeling. This is another method that you use in the studies. But before everything else, because this background noise measurement, this 20 minutes measurements, is very common and very cheap and very popular and effective, so we decided to compare the results of this highly used method with whatever is recommended in National Building Code. This graph shows this is the fundamental site period. This axis shows based on the National Building Code. This is what you get from H/V, or this lunchbox measurements. It is in a good shape when you are dealing with the thin soils. When you are dealing with the thick soil, the lunchbox deviates from recommendation of National Building Code. They don't match. Which one is right, which one is wrong, we don't know. That's a question that we are going to work on it. Okay, so we apply different methods. Mainly we focus on finite element modeling for AD-GAL for the city of Ottawa. The reason that we work on AD-GAL, because AD-GAL is the threshold between the gray area between linear soil and nonlinear soil. Also, we did some modeling for 400 GAL. 400 GAL, or 400 centimeters per second square, is the design earthquake for the city of Ottawa. So we did all of these simulation, and this is what we get. This is T0 based on, or fundamental site period based on National Building Code. This is what you get using the launch box or H/O ratio. This green line shows for 80 gals, or centimeter per second square, which is the gray area between linear and nonlinear soil. And this red line is 400 gal, which is the fundamental site period when an earthquake happens. So when you go there and measure the fundamental site period, you are just using background noise, which is a very elastic behavior. When an earthquake happens, based on this, 400 gal is the nonlinear area. They don't match. Here I'm not going to say which one is right or wrong. The good news is we can find the relationship between these. Again, still we can go out there using this 20 minutes measurement to come up with the fundamental site period based on the launch box. I say launch box, it's a very small one, we call it that way, and do some simple calculation and come up with the fundamental site period for the design earthquake. This is done for the city of Ottawa. It may or may not work for the other cities. This is the answer we don't know. But because in the National Building Code, the fundamental site period is based on this simple equation, the thickness of the soil, the average shear wave velocity of the soil, then we applied all of those shear wave velocity measurements to 21,000 boreholes available that we have, and we came up with the fundamental site period for the city of Ottawa. The Gatineau Park City Hall, and in this area, this will be done this year, hopefully, or maybe in the worst case, next year, this will be finished. The City, Ottawa, Gatineau Hall, both of them. This is new measurement. This is a new outcome. The question is it possible? Because measuring VS is not an easy job. The easiest way is just go to do a 3 or 4 hours with the $40,000 instrument, 3 students. Oh, that's it. Doesn't go away. Oh, okay. So the idea was, is it possible to use this 20-minute measurement, which is just very simple, and find the shear wave velocity? This is what we have done for around 200 sites. So again, there is a nice relationship between VS30 and fundamental site period using the launch box. So this is a shortcut. We don't call it accurate because we can use this method to estimate VS30 at this moment. So we just go there, find the fundamental site period, and using this equation, we can come up with the average VS30, which leads you what you should expect when you do the real seismic measurements. Okay, let's look at some earthquake observations in the city of Ottawa. In Orleans, this is the east of Ottawa, Orleans area in east of Ottawa. There are 2 stations here. One of them is on the bedrock here, and about 1.5 kilometers away from this, we have another seismic station, identical seismic station on 90 meters of soil. So it's a very nearby station, one of them on bedrock and the other one is on soil. This is what we record. The difference, the red one is, this is for the earthquake 77 kilometers away from the Ottawa, Val-de-Bois, magnitude 3, 2008. The red one is what is recorded on the bedrock. The black one is what is recorded on the soil. You can see there is a huge difference between these two. This is one of the east-west component, north-south component, and the vertical component. The amplification is huge. It is unusual compared to amplification that you can expect based on the National Building Amplification Factor, which is around 4. So that was a question, why this is happening. Again, those are very small earthquakes. The soil behaves very linearly, but when it comes to big earthquake, we expect big earthquake in Ottawa, as John mentioned this morning. Based on paleoseismology studies, there were 2 large earthquakes, one of them around 45, 50 years ago, 4,550 years ago, another one 7,000 something years ago. So these earthquakes, based on the paleoseismology, they have around magnitude 6 to 7. And also the aggregation figure for the city of Ottawa suggests that we should expect magnitude 6, 7, 7.5 for this, in that area as well. But the good news is the return period of these earthquakes are really quite a few thousand years. This is the amplification factor given by the National Building Code. Class E divided by Class A is a factor of 4. This is the amplification factor that we get based on weak motion recording in the city of Ottawa, 2 nearby identical seismic stations. You can see the amplification factor as high as 100. This is huge. And there are 2 things that are happening here. Again, the soil is linear. There is no damping at that level. The second one is the contrast ratio that we have in the city of Ottawa, which is the contrast ratio between the soil and the bedrock, is around 20. These are 2 factors which are affecting this one, plus one other factor that I'm going to talk about that one later. So this is the strong motion that we had from Waldeboro earthquake, 2010. Today, you have seen quite a few slides about this earthquake, magnitude 5. 50, 60 kilometers away from the Ottawa. If you look at this, this is the recording from John Adams' slides, a copy of John Adams' paper and a slide. It gives you the PGA at different stations on soil and on the bedrock. If you just, I'm going to compare these two. In National Building Code, the ratio of A to B site class is around 1.1. Whatever is seen by, has been seen on the Waldeboro earthquake is around 2. In National Building Code, the ratio of A to C is around 2. Waldeboro earthquake was around 2 or 3. In National Building Code for A to D, the best site class to last site class, or E, in National Building Code is 4. Waldeboro earthquake is around 1, 2, 3, or 4. But this is not enough. Usually, we should have quite a few hundred observations to make any conclusion, to say, okay, the site amplification in city of Ottawa is not following whatever is recorded or is following whatever is recommended by National Building Code. So we are in the dark here. So we have done quite a few measurements or studies to find a solution, and we are still working on it. There are 2 concerns here in Eastern Canada, or at least in Ottawa. Again, the contrast 20, very loose soil. And if you look at the equation that is mainly used by most of National Building Codes, not just Canada, you can see it. They started from this simple equation. This 10, 50, 10, 50, this is the average shear wave velocity of the bedrock in California. The average shear wave velocity of the bedrock here in Ottawa is 2,700 and 2,700. The average shear wave velocity of the soil in California is quite a few hundred, 300 or 400 meters per second. In Ottawa is 150. So these are the big questions that we are dealing with, and we don't know the final answer, but we are working on it. This graph shows the sensitivity of the amplification as a function of the level of shaking. If you remember, all of our observation that we have so far is a weak motion, and the only strong motion, again, it's not a strong motion, weak motion that we have is a wall earthquake. So we have to do some simulation to go with this to a stronger level. So we came up with, using finite element modeling, we came up with this equation which shows the seismic soil amplification for the fundamental frequency as a function of level of shaking, PGA, and as a function of contrast ratio. This graph shows the contrast ratio. This shows peak amplification for the fundamental frequency for different input, 23 to 349 centimeter per second square. And this graph shows the effect of nonlinearity. When you increase the level of shaking, the peak amplification is reduced. So based on whatever we have found so far for the city of Ottawa, the shear wave velocity of the bedrock, the shear wave velocity of the soil, which is unusual, or I don't say unusual, they are quite different from West. We have done some soil modeling and compared with the National Building Code. The only missing parameter here is the damping for the soil in the leader clay. We don't have leader clays damping yet. We are working on it. If we just follow the typical damping that you use in daily exercises in geotechnical engineering, this is what we get for soil amplification for this in Eastern Ottawa compared to whatever is given by National Building Code. As you see, for the Class D, the difference is around 55%, and for Class A, the difference is around 30%. So damping is an issue that we are working on it. And one of the methods that we have done so far is in situ measurement. Simply send two sensors, one of them at shallow, another one in the deep level, start shaking the ground based on the amplification difference in amplitude of these two recording sensors, which come up with the damping. And this is, again, at the low level of the strain. The soil is linear. This is the GSC mini-vibe and people who are working on this one. And also we have started working on damping of the leader clay at higher level of strain, and we have a collaboration with the University of Waterloo using non-resonance column to come up with the damping. And the only question that we have in our measurements is damping to find the answer, and the final answer is if there is any difference between National Building Code amplification factors and what is really tailored or customized for the city of Ottawa. Thank you very much.